Hello, warriors. This is Miss Lemons, and today we are going to be talking about phase changes. So make sure you have your phase change notes and practice out. So first, we'll talk about states of matter and the phase changes to get between them. Let's talk kinetic molecular theory. We're going to watch this video, but the audio isn't great on it, so I'm going to do the voiceover for it using closed captions. The kinetic molecular theory is the theory that all matter is made up of atoms and molecules that are always moving. These particles hold kinetic energy and move around in random directions. In higher temperatures, the particles have high energy, and in low temperatures, the particles have less energy. The more energy a particle has, the faster it will move. In solids such as ice, the particles hardly move at all and hold a regular pattern, because the energy is low and the particles are tightly packed. In liquids such as water, the particles have more energy and the freedom to move around. Liquids have the ability to flow and fill the shape of any container they are put in. In gases like steam, the particles have the most energy. The particles move around freely, and gases are usually invisible to the eye and can be expanded and compressed in different temperatures and pressures. All matter is composed of atoms and molecules that are always moving. The higher the temperature, the more energy these particles have. And that is the kinetic molecular theory. Okay, so matter is made up of particles that are in constant random motion. The motion of those particles is called kinetic energy, or the energy of motion. And the average kinetic energy of a substance is its temperature. The temperature also helps us determine a substance's state of matter, so solid, liquid, or gas. This is also a really great video. It summarizes the properties of the three states of matter. We are not going to watch it in this video today, so take some time later on to maybe view the video on your own. All right, so we've got this awesome little table here. You're only really filling in this last column, and that's really the part that we're going to be focusing on for thermochemistry. The rest of this table is going to become more important for gas laws. But if you think about it, it kind of makes sense. Solids have a definite shape and a definite volume, like my water bottle here. I can't change its shape unless I really add a lot of energy into it. The particles are going to be stacked very close to each other, but the motion is going to be very slow. If something has a slow kinetic energy, that means it's going to have a low temperature, which means it's going to have a low temperature, and it's going to be losing energy, right? If something is a liquid, it's going to have an indefinite shape, right? I can pour this into a bowl. I could pour this into a Dixie cup. It's going to take the shape of its container, the liquid inside. The spacing between those particles is moderate, and so is the motion. So they are moving around, they're flowing past each other. And gases, if you've ever taken a balloon, fill it up with your air, you can take that balloon and you can squeeze it, and that's because gases don't have a definite volume. You can compress them. The spacing of those particles is going to be really far apart and super, super fast, which means we have a high temperature. All right, the notes. Phase changes are physical changes, which means that they are reversible. During a phase change, a substance changes state of matter to solid, liquid, or gas. The identity of the substance does not change, but the energy does change. Phase changes absorb or release energy just like chemical reactions. The change in energy associated with a physical change or a chemical change is called enthalpy and is represented by the variable delta H, or the change in enthalpy. When energy is absorbed, the particles increase their kinetic energy, causing them to warm up. These types of phase changes have a positive delta H. When energy is released, the particles decrease in kinetic energy, causing them to cool down. These types of phase changes have a negative delta H. You also have these three letters drawn at the bottom of your page. Go ahead and add in the arrows. I personally would color code them if I were you, so pause the video to get your supplies out if needed. All right, so first, going from solid to liquid is called melting. Liquid to gas is vaporization. And then solid to gas is called sublimation. A good example of that would be like dry ice. Going from gas to liquid, we have condensation. Liquid to solid, we have freezing. And then gas to solid, we have deposition. Now, you'll notice that the delta H for sublimation, melting, and vaporization is positive. That's because we're putting energy into the system. Whereas for freezing, condensation, and deposition, the delta H is negative, and that's because we are removing energy from the system. So let's talk about each individual phase change and add it to our notes. Melting. We are going from solid to liquid. We require energy, or we absorb energy, which means we're going to have a positive delta H. The particles are going to increase in kinetic energy, which means we're increasing in temperature, and they're going to break from their fixed positions. The melting point is the temperature at which a solid changes into a liquid. And both states of matter, solid and liquid, are going to be present at the same time during the melting point until all of the solid melts. You can see here that this ice cube is sitting in a puddle of its own water. Solid and liquid are existing together. Vaporization, also known as evaporation and boiling. That's going from liquid to gas. It does require energy, or absorbs energy. We have to put energy into the system, so it's endothermic. That's going to be a positive delta H value, which means we're also increasing in kinetic energy. And if we increase in kinetic energy, we're also increasing in temperature. When they increase in kinetic energy / temperature, they're going to start, those particles are going to start breaking from their original positions. The boiling point is the temperature and pressure at which a gas or liquid changes into a gas. And both states of matter will be present until all of the liquid vaporizes. So you can see in this boiling pot of water that the water is still liquid at the bottom of the pot, but there is steam on top. So both of them are there until all of that water evaporates. Freezing, solidification. So we're going from liquid to solid, and we are removing energy. Energy is exiting the system. So we're going to be releasing it. That means negative delta H. The particles are going to decrease in kinetic energy, which means that, one, we are also decreasing the temperature. That means that the attraction between those particles, because they're not moving as fast, they're going to be more attracted to each other, and they're going to be moving less. The freezing point is the temperature at which a liquid changes into a solid. And freezing and melting actually happen at the same temperature. It just depends on whether you are putting energy into the system or taking energy out of the system if you are freezing or melting. Plus, during freezing, we know that both states of matter are going to be present until all of the liquid freezes. Condensation, going from gas to liquid. This is going to release energy, right? And that means a negative delta H. That's exothermic. If we release energy, the particles are going to decrease in kinetic energy, and they're going to start to clump together, which means the attractive forces between them will start to increase. This also means that the motion is going to decrease. If we see a decrease in kinetic energy, a decrease in motion, that means we're also going to have a decrease in temperature. The condensation point is the temperature at which a gas changes into a liquid. And vaporization and condensation are going to be happening at the same temperature. So both states of matter, the liquid and the gas, are going to be present at the same time during the condensation point until all of the gas has condensed. Okay. Phase diagrams. We are going to label the phase diagram that you have on that page, the next page. Let me just walk you through it. So if we look at this phase diagram, we want to pay attention to the X and Y axes. So on the X axis, we have temperature in degrees Celsius. And then we also have pressure in kilopascals. So it gives us the temperature and pressure. And for any given substance at which they exist as solid, liquid, or gas. Section of the diagram represent each phase of a substance. So state A, state B, and state C, you can see that we're kind of broken up into 3 different chunks here. Each section represents a different state of matter. The line that separates the two phases or states of matter indicates the conditions for a phase change. So if you're anywhere on this line, you are actively changing phases from solid to liquid, liquid to solid, etc. The triple point is where we see all three of those lines intersect. And this is the temperature and pressure at which all three phases exist at the same time. So solid, liquid, and gas happening all at the same time. So solids are going to have the lowest temperature and the highest pressure because they're really tightly packed and they are frozen. So your solids are going to be in this first section. Gases have the lowest pressures. So gases are going to be down here in the third section, whereas liquids are going to be in the center. So if we're going from solid to liquid, if we're on this line anywhere, depending on which direction we're moving for increasing temperature or decreasing temperature, we could be actively becoming a liquid or actively becoming a solid. But if we're on this line, we are actively changing phase. We are going to be solid and liquid at the same time. If we are on the other two lines, the same idea is true. We've got liquid to gas, so we would have both liquid and gas existing at the same time if you land anywhere on this line. And same idea for this little golden portion of the graph, that if you land anywhere on this line, that solid and gas is going to be existing at the same time. So make sure we're also adding in our different phase changes. So if we go from solid to liquid, we know that as melting, or it's also called fusion later on. And if we go from liquid to solid, we are freezing, also known as solidification later on. If we go from liquid to gas, this is called boiling or vaporization. And if we go from gas to liquid, this is called condensing or condensation. If we go from solid to gas, this is called sublimation. We actually aren't going to be dealing with a lot of solid to gas or gas to solid, so sublimation or deposition, so you don't need to worry about that. All right, in a different video, I have already gone through these questions, so if you need help on the questions underneath your phase diagram, check out those videos.